All right, guys, so welcome back. There's relatively many of you guys for a non-quiz day. That's great. Thanks for shoving your way through the quantum class. Get in here. Right, so let's see here. In terms of announcements and things, finally, my exam announcement, I think, is becoming actually relevant to your lives. So your midterm is, what, about 10 days from now-ish, plus or minus? So, you should study, would be my advice. Yes?
Which lecture is the last one that material will be on?
Which you are responsible for any graphics material that we cover up to and including the second before that quiz. Yeah. And to the person who asked me if you're responsible for the lecture material after the quiz, come on, Nick, I have so much email. Yeah. Yeah, so we will post, actually we can do that today if you don't let me forget. We can post all the old midterms for 837. Every year the midterm is at a slightly different point in the semester because essentially we just tune it to whatever the drop dead date is. So obviously if there are questions on those midterms that cover things that are not on your calendar for the midterm date, we're not going to ask you about it. There's no reason to email me. But yeah, the exams have been pretty consistent in terms of their format and content, so it'll give you a pretty good idea. Any other questions about that? And remember, again, that same week your project proposals are due. Just write it now if you're concerned about that week. Okay, and other than that, oh yes, yeah. The same time as your homework, I don't know, maybe 8 or something? Oh, you mean the midterm? Oh, I'm sorry. I thought you meant your proposal. Yeah. Yeah, the midterm's during class. Yeah. Any other questions here? And I think your last homework is already out. Is that right? Yeah. Your last homework is the graphics hardware homework. This is the one that fails on everybody's machines. Because you guys have already experienced how hard it is to compile OpenGL code on your personal laptops. I know because I get the union of all of your problems in my office. So even if you've gotten the past assignments to work and you're like really confident, you're like, okay, cool, like I'm really good at graphics and like I got the first one to compile, so like now I can procrastinate. I would not recommend that here because we're going to be using shaders and stuff, and these are the sorts of things that just work like ever so slightly differently on different machines, and you don't want to discover that the day before the deadline. The other thing to know about coding shaders is that they fail silently. This is an annoying species of coding where it's not, even if you have like a compile mistake, you may not receive an error. So this is particularly like one thing that you really should test on the Athena machines, right? That's our official policy, and that's a good one here because like it might be that you have a bug that somehow in your code is just going unnoticed on your laptop, like it's gracefully taking care of it anyway, and that's not a thing we'll be able to judge. Cool. Any logistical questions? Fabulous. All right, so starting today, we're going to complete our transition from ray tracing into a different type of rendering algorithm known as rasterization. I think we've foreshadowed that for a long time coming in this class, and now it's time to dive right into that. Essentially, from 1,000 miles away, ray tracing is really cool because it's easy to code and it's easy to capture all kinds of physical effects, right? I mean, essentially the last couple of weeks we went down our long list of like things that a person could do to light and shown how to capture each of them in a ray tracer. What we're going to see in rasterization is the typical trade-offs here are designed to make our rendering fast, right? So rather than thinking about applications and like movie effects where you can wait for the rest of your life for your like fancy subsampled anti-aliased global illumination whatever algorithm to converge on a very subtle lighting pattern, now we're going to do like the sledgehammer of computer graphics and do these things that need to run at 29.97 frames per second, because anything below that and your eye is going to notice a flicker, and that's bad news in the real-time rendering world, right? And of course, these kinds of algorithms are completely different, right? They're tuned for graphics hardware, which is quite different from your CPU. And so the type of parallelism, the types of pre-processing, and all that good stuff is just quite different. Although, of course, the math that's sitting behind it is pretty similar, right? So the question that we're going to be answering the next few lectures, and then we're going to have our like fun grab bag of random graphics topics that don't fit anywhere else, is essentially how do you render interactively, right? So one thing that you probably noticed in your ray tracing assignment is that it is the opposite of interactive, right? You had like a command line interface, you hit a button and it just sat there and crunched for some time. That makes for a really boring video game. Although nowadays it does. In my day, we had these, what was it, Myst and all these kinds of games where they just pre-rendered all the frames and they were just stored on your computer, and essentially it was just like a glorified PowerPoint, which was about where my video game skills dropped off. But in any event, these days, when we want to render interactively, we need to use tools like OpenGL or DirectX, which is a Microsoft product, whose job in life is to generate not necessarily the best image, but an image that is fast, right? And so these types of renderings tend to not capture some of the really complicated effects that just in a few lines of code in our ray tracer we're able to get, right? Like the reflections and shadows and stuff. Because what we're going to see is that for each one of those effects, we're going to need like a very specialized graphics card trick to capture it. Like somehow it doesn't, ray tracing is really elegant in that you implement one piece of code, intersecting array with the scene, and then with like essentially a little bit of lipstick, you can make it do a lot of other things. That's just not going to happen here, right? It's just going to be a lot of different tricks, each one of which tends to be like kind of a weird indirect way to capture some effect that you want. Okay, I'll give you the sort of facetious introduction to the difference between ray casting, ray tracing, and GPU-based rendering or rasterization. Remember the ray casting algorithm that we've already developed in this class, and now all of you have implemented, you're all experts. Roughly, it looks like the following, right? Which is you iterate over all of your pixels on the outside, you generate a ray, and then you iterate over maybe all the triangles in your scene or your objects. And then for each one, if the ray hits the triangle, you keep the closest one, you iterate. Yep. And I think we're all pretty darn good at that basic technique at this point. The rasterization algorithm does something slightly different. It just flips the two outer for loops into a different order. So now, like when I ray trace an image, my outer for loop is over the pixels, right? So for each pixel, I determine its color, and then I move on to the next pixel. Okay, like maybe I can parallelize, but that's whatever. In the rasterization algorithm, instead of doing that, I'm going to draw things one object at a time. So I'm going to draw like the first triangle, and then the next triangle, and then the triangle after that, which I think is reasonable. I mean, I think oftentimes when you ask people to like draw something by hand, that's roughly the algorithm that they follow. But now the kinds of issues that we're going to have to deal with are quite different, right? So for instance, in a given pixel, figuring out what triangle is on top is going to be a little bit more tricky than it was before, right? Because before you just look over all the triangles and choose the closest one. Now we're going to hit every pixel multiple times for each triangle in our scene, and we're going to have to keep track of information like depth. But anyway, at least sort of superficially, the difference between these two algorithms is just a matter of flipping these two for loops. But of course, this is kind of a goofy comparison, that essentially, remember this was like our first lecture on raycasting, and then the very first thing that we did was we defined a bunch of different algorithms whose job in life was to take this inner loop over triangles and make it really, really fast. Right? We talked about different like spatial partition trees, all that good stuff. If that loop is on the outside, all those tricks for making the inner loop faster are now irrelevant. Right? And so now we need a whole new set of ways to accelerate this inner loop to make it really fast instead. So that's the sort of 50 miles away perspective. I should pause for a second. Are there any questions about the basic point here? We're going to draw things one object at a time instead of one pixel at a time. Cool. All right. And the basic sledgehammer for doing rasterization is the GPU. This is your graphics processing unit, which is a thing that is probably in all of your computers. To some degree, I mean, most of these laptops are too thin to hold a heavy-duty GPU, but companies like Intel make these things that are called integrated graphics, which are like little graphics cards that are attached to the side of your CPU. And of course, those of you who have these like big, heavy laptops that are like blowing steam out of the side and like, this kind of like punk look to them, may have an actual graphics card, which is what you need for video games. And it's all about throughput, right? That's the difference when you compare these different cards. It's just like, how many objects can you shove into this pipeline, how fast, and how many pixels do they output? And the bigger the number, the better, except for trees, because they use up a lot of electricity. But in any event, right, so the basic vocabulary words for today, in addition to GPU, to graphics card, graphics processing unit, is rasterization, which is just the process of taking a pixel, or a triangle rather, I suppose an object, but typically it's just triangles, and figuring out what pixels it covers. Right? So in other words, like, I give you a can of paint, I give you the coordinates of the triangle, and now your job is to paint the inside. And the algorithms that we have for that so far are not so great from a rasterization perspective, right? Like, what would you do? Like, if you were to take the ray tracing perspective, maybe you go over every single triangle in your scene and check if the pixel is inside the triangle, and then that's how you would light them all up. But of course, that's, computation time proportional to the whole grid, which is not terribly efficient. Okay. And so that's the basic thing, is that rather than just checking every single pixel, which one's inside the triangle, we're going to come up with more clever techniques. There are a lot of different words that basically mean the same thing. Another one that kind of dates back to 1970s style video games is something called scan conversion, which is another term. I think scan conversion is specifically this process of figuring out which things are inside of a triangle and which ones are not, as opposed to then also deciding on the color and all the other stuff that happens when you render. This dates back to really, really old displays, which really did follow scan lines. So scan line is like a line of pixels, right? And it used to be that your old display, what it would do, it had this like kind of laser-looking device. I'm a theorist. I don't know what the hell is inside of these things. But there's some object that generates light and kind of goes back and forth like that. And so really it was scan conversion. Like, it was trying to figure out on the fly, as this object is sweeping across your line of pixels, whether it should light up or not, to display this thing as a triangle. Right? That's why, like, if you watch videos of these old computer screens, you can kind of see lines moving up and down, because that's the way the display worked. These days, your computer screens are doing much more complicated stuff than those old things, which is good because they required a whole tube worth of space. Right. During scan conversions, rasterization, whatever, again, in this class, I'm not big on these vocabulary words because I feel like we use them very loosely anyway, so I wouldn't be too hung up on the difference between these terms. But in any event, we're going to introduce one really key object, which is sort of the piece of technology that makes rasterization work. That's something called the Z buffer. Anybody heard of the Z buffer? Yeah. So essentially, so far, when we render images, what do we render? We render color, right? We render red, green, and blue. Somebody's letting the steam out outside of our classroom. Right. In addition to that, what we're going to rasterize is, yeah, it's color, right? We're going to, as we paint these triangles, we're going to actually just, decide what color they are. But other than that, we're also going to keep track of depth at every pixel. Why do you think we do that? Yeah. Exactly, because remember, now we're drawing stuff one object at a time, so we're going to hit the same pixel multiple times. So now, when I render a new triangle, the first thing I do is I say, aha, like this pixel is inside of the triangle that I'm rendering. That doesn't necessarily mean that I want to actually put that color there, right? I have to make sure that it's on top of whatever I drew last time, right? And essentially to do that, we're going to need that Z buffer, right? So it's a very typical thing to do. So we don't display it on the computer screen, but we do keep it behind the scenes as an additional piece of information that's useful. In fact, Z buffer is going to be our first example of just buffering more generally, which is to say that one of the kind of key techniques in rasterization is going to be just to like rasterize the heck out of everything in your scene. So for instance, we're going to talk about drawing shadows. In fact, you're going to implement it on your homework because I'm evil and have you guys do that, even though it's like really awful to implement. And the way that you're going to rasterize shadow is you're first going to draw the scene from the perspective of the light bulb, right? Because that's what's going to tell you what object is closest to the light. And then you're going to draw the scene a second time from the perspective of the camera. And you're going to use that first guy to figure out what things are in shadows and what aren't. Right? Which is a fun little piece of math to do. Okay. Right, so what are the main differences between these algorithms? There are many. First of all, what needs to be stored in memory? Like, what do I have to keep around when I'm rendering? Well, if I'm doing ray casting, every single pixel, I generate a new ray, and then what do I have to do? I have to touch every object in my scene. So I have to keep in my graphics memory, what? A list of every single triangle. Is that needed in rasterization? No, I'm just drawing things one triangle at a time. I pick up that triangle, I draw it, and I can just throw it away, right? And that's part of the reason why these things can be so efficient in the graphics pipeline, right? Because essentially the real-time graphics pipeline is all about throughput, and essentially I can just throw that information away after I draw it because it's irrelevant. And so the memory requirements are typically much less for these kinds of tools, right? So the rasterizer only needs one triangle at a time, of course, plus the entire image and the depth. The ray tracer, I suppose, doesn't have to store the whole image at the same time if you had like a really giant image, but I think it's pretty rare that you would ray trace something that's so big that modern computers couldn't just keep it around. Does that make sense? The memory demands of rasterization are much, much lower. Okay. Right, and so the basic advantage here, I guess, is what I just said, is that essentially modern scenes are way more complicated than modern images, right? Like your graphics card can easily store a megapixel image, and moreover, it's sort of a regular, it is a space regular representation, right? It's just like a nice grid of numbers. It's a 2D array, an image, whereas like a description of a scene is this like wild and crazy thing with pointers every which way and like probably a binary space tree that's like, you know, hard to organize and maintain and traverse. So whereas like your access here is probably nice, coherent memory access moving up and down, you know, the lines of pixels. When you're ray tracing, you're like constantly making these demands of your computer's memory to like grab stuff from different places and jumping around in your storage. And so rasterization-based rendering is this sort of clever technique where you're just streaming your triangles one at a time. And when you implement these things, it's exactly what you do. You like generate big piles of triangles, you jam them into the GPU, and then while the GPU is doing its thing, your CPU is like busy, you know, managing your AI in your video game, generating the triangles in the next frame, all that good stuff. But there are limitations, right? So ray tracing, for instance, ray tracing a sphere is easy. We did it in this class. I think you implemented it, I forget. Rasterizing a sphere is not so easy. So rasterizing arbitrary shapes is a little bit tricky. Every time you have a new shape, you need to come up with a new scan conversion algorithm that tells you what pixels are on the inside in a very efficient fashion. And moreover, the types of shading computations that you can do in rasterization are quite different. So for instance, remember your graphics card is this like hammer that just like wants to hit a bunch of nails. I keep referencing this like, you know, clip from I Love Lucy that probably none of you guys have seen, you know, where they're like packing pills on the conveyor belt and they're moving past and like the conveyor belt keeps getting faster. That's sort of what your graphics card's job is. But so for example, would it be so easy to draw reflections off of that sphere? Probably not, right? Because some pixels have reflections, some don't. And that's the kind of thing that rasterization cannot handle particularly well. In fact, just reflective surfaces in a rasterized setup is already actually pretty tricky to implement. Right, so the advantages of raycasting and ray tracing are that you can just render arbitrary scenes. The complexity per pixel can vary widely in a scene, and that's not such a big deal to deal with. The disadvantage is that it's expensive, and it's hard to do SIMD style processing. Does anybody know what SIMD stands for? It's going to come up a few times in this class. Yeah?
Single instruction, multiple data?
Single instruction, multiple data, exactly, right? Where Lucy is packing the same pill into multiple, you know, pill boxes, one over, you know, so essentially just doing the same operation over and over again, rather than like this pixel needs reflection and that pixel over there needs refraction. Those are the sorts of things that rasterization algorithms cannot handle particularly efficiently. Okay, any questions so far before we dive into it? I think the high-level ideas are nice. In fact, I think rasterization in general is conceptually simple. The big headache is going to be that like nobody actually implements rasterization algorithms. They're just built into tools like OpenGL. And OpenGL is so close to your graphics card that just interfacing and working with it is a headache, right? To me, at least, that's the hardest part. Okay. Right, so our typical kind of modern real-time graphics pipeline, right? We have as input here, you know, a geometric model, like our favorite Stanford bunny, information about the lighting in your scene, your viewpoint, and so on, and we're going to output color. Obviously, we've already talked about this in the ray tracing world. Now we're going to go back through this pipeline in rasterization and see what we can say about it. So the steps of rasterization look quite different from ray tracing, even if you were to sit down and implement the basic version. So essentially, the basic steps here, for each triangle, remember there's an outer loop that I haven't even listed here, which is where all the objects in your scene. The first thing you're going to do is actually just project the whole object onto the computer screen. You're going to, because in some sense there's no reason to rasterize a 3D triangle. You might as well just project it and draw something on the plane of the screen. It's actually something that I think is neglected. Most of the computations you do in rasterization are just two-dimensional stuff after you put it onto screen coordinates. Then you got to rasterize the object, meaning you got to figure out what pixels are lit and which ones are not. Then you, once you've figured out the list, you've generated a list of fragments is the term we often use in OpenGL. That's like the list of pixels that intersects the triangle that you're about to draw. The next thing to do is run your fragment shader and determine the actual color. And then these two sometimes get mixed together, but like essentially you got to determine the color and then you got to determine whether I actually want to, you know, draw it or not. Like, and in fact, there's a lot of wasted effort that goes into these rasterization tools. You tend to rasterize the entire triangle and then look and say, oops, that triangle is actually behind the stuff I've already drawn. And so some of the techniques we'll talk about, like clipping, their job in life is to, if I can eliminate an entire triangle, like I can decide that like I really don't need to rasterize this object, then maybe I don't even need to send it to my graphics card. Okay, so anyway, yeah, that's our basic thing. So we project our vertices. Then we got to rasterize this object. We'll go into more detail and so on. And then finally, the visibility in the Z buffer is a really key object. This is just like T-min in your ray casting algorithm, right? That's the Z buffer. In fact, it doesn't really matter if I keep depth. I just need something proportional to depth. So like T would be fine. And so essentially, somewhere in your code are these 3 lines of code, right? That are saying if the Z that I just got from my new triangle is less than the Z that's already in the Z buffer, keep what I just did and otherwise throw it away. Okay, and that's it. That's our basic piece of pseudocode, and it's full glory here, which I think, again, I don't think conceptually is too difficult. Any questions about the sort of high-level algorithm here? Cool. All right, so let's go in a little more detail. So we already actually talked about projection, but your midterm's coming up, so we might as well review for just a few minutes here. The difference here is that when you do ray tracing, your objects are all just in 3D, right? Like you don't, we talked about homogeneous coordinates and all that stuff, and then notice that I sneakily like really didn't use them all that much. Because in ray tracing, your objects are just sitting in the world around you, and your ray is a 3D thing. So this is the only 2D part of ray tracing is generating the ray to begin with. That's very different here, where your rasterization is in screen coordinates, right? Like even if I have a giant triangle, if it's like kind of skew away from my screen, it might not take up that many pixels. And I might as well account for that, right? And so the way that I'm going to do that is take those vertices of the triangle and then project them onto my computer screen before I do that computation. And we already talked about a lot of different ways to do that. So when we talk about scan conversion, typically the scan conversion algorithms actually only really work for orthographic projections. The reason for that is that when you project your objects in your scene, you also maybe rewarp your geometry so that what used to be your ViewFrustum, like this funny cone coming out of your eye, which is all the stuff you can see, we're just going to kind of reshape into a cube so that orthographic projection works. We'll talk about that more in a second. So remember what this looks like, right? So essentially your camera, as you move farther and farther away from the camera, the field of view that you have is larger. And so when you want to project onto the scene, roughly you need to divide by depth, right? And this is assuming that you have this sort of virtual computer screen at z equals 1. And we covered this kind of clever idea in homogeneous coordinates, which is that if we identify vertices based on whether they're constant multiples of one another, then we can actually think of camera projection as a linear operation by taking the z value and kind of copying it into the homogeneous coordinate, which secretly is like dividing by z, but we didn't see it in this form. Okay, so, right, and of course extending to 3D is no harder, right? You just end up with an extra coordinate. Okay, so, right, there's one caveat when it comes to rasterization, which is that these projection matrices, the way that we've defined them so far, they just throw away depth, which is like not so great. Right, because essentially when we talked about projection so far, our task was what? It was just to figure out where on the computer screen this 3D point is. But we actually want to keep track of depth in our rasterization pipeline. And so essentially what we're going to do is we're going to take our original coordinates in 3D. Those are not super useful. And we're going to move them into new coordinates, where the first two coordinates are going to be the position on your computer screen, and then the third coordinate is going to be depth. Does that make sense? So essentially, what we're going to do is just a change of coordinates so that the first two guys are what we need to do rasterization in screen space, and then the third one is what we need for the Z buffer. And so this is really no more complicated, right? Essentially, by the way, typically people store 1 over depth for precision reasons, but that doesn't matter so much. But it looks like the following, which is that essentially we'll take our W coordinate from before and copy it in here, but still put just a 1 here for your Z coordinate. And then what is that going to do? Well, when I homogenize, when I divide by Z, I'm going to get the position on the computer screen and then some number that tells me about depth. And that's good enough. And so geometrically, you can kind of understand that using this schematic picture here, where you have this object. We call this the ViewFrustum, which is like, you know, that little cone coming out of your eye, maybe clipped at 2 different planes. And then what I'm going to do is I'm going to map that object to a cube, right? And so essentially when I divide by Z, I'm taking this shape and then converting it into a cube. And I'm just leaving the depth alone, so this coordinate is still here. Again, this is the kind of math that like it's complicated to describe in words, but if you just write down the equations and kind of stare at them for a minute, you'll agree that this is essentially the model that's going on. And so the reason to do that is that now rasterization is not so hard, right? You just ignore that third coordinate and you do like 2D painting, and the third guy gives you some information about depth. You have to be a little bit careful. When you rasterize the depth buffer, you need to make sure that when you interpolate that value across the triangle, it's actually the depth and not like some other thing because you computed the reciprocal. But that's just a detail. Okay, so let's go into a little more detail here. So here's our ViewFrustum picture, right? Typically in OpenGL, which is the standard that we'll talk about. By the way, today we're going to talk a little bit about OpenGL, and mainly when I talk about it, it's going to be the OpenGL 1.0 standard. And the reason for this is not that it's the standard any of you guys should use. It is very out of date. But the old graphics pipeline, they used to just define like, this is the near plane, this is the far plane, this is what clipping and so on are. These days they've removed all those features and they make you implement them yourself. But most graphics people still follow that convention anyway, just because it was the first convention that was out there and there's no real reason to change. In any event, when you want to specify your ViewFrustum, typically you have some angle, which is your angle of view for your eyeball. And in addition to that, you have 2 planes, which are the Z close and the Z far. And what you're going to do is anything that is outside of these 2 planes, you're just not going to rasterize. And there's a couple reasons for that. One is if I'm storing 1 over Z instead of Z, what's going to happen if like there's an object right on top of my eyeball? Well, that number's going to explode, right? And so having a clipping plane that's close to your eye and one that's far away gives you sort of a range of precision values that you need for your depth buffer. Because what we're going to see is that there's certain artifacts that can happen based on just rounding that happens in the graphics card. And so there's a lot of conservativeness about like using every bit that you can, right? So if you know the range of Z values, then you can kind of rescale to make use of the entire floating point range of numbers instead of wasting a bunch of bits in computations that you don't need. So they're like sort of arbitrary, but they just bound the precision that you can resolve depth at. Okay. So after you map into this object, we call this the canonical view volume, which essentially is going to take your Z values between -1 and 1, and then your X and Y coordinates also between -1 and 1. Now you're in good shape for rasterization, right? Now you just draw. Here's the particular matrix that does that. So essentially all that we're doing here is we're taking the far plane and mapping it to Z equals 1, near plane and mapping it to Z equals -1. And if you kind of work through the computation, you'll see that's what ends up happening here. Okay, so right, why do we do all this stuff? Essentially, this is all one giant step that we call projection in the graphics pipeline. And its job in life is just that objects, just like we've seen over and over in this class, are all on their own crazy coordinates. And your job is to put them in the coordinates of the screen because from the rasterizer's point of view, all these details about how you chose to represent your 3D geometry are irrelevant, right? This is just a sledgehammer that wants to turn on pixels. It doesn't care about the fact that like you stored your car and tire coordinates or whatever. Right? And so that's essentially what's going on here. A very typical thing in the, again, OpenGL 1.0, now you can do whatever the heck you want, standard, was to separate your transformation into two matrices. This is a very typical thing. There was model view and projection. And the idea was, remember on what is homework 2, you were like traversing up and down that system of joints. And as you're doing that, you're like pushing matrices onto your stack. So you had one matrix that was taking you from object coordinates to world coordinates. And then there's actually a second matrix, which in that assignment was irrelevant, but now becomes relevant, which is taking you from world coordinates to computer screen coordinates, right? And so essentially, this was sort of a nice factorization, was to have both of these guys around. The reason being that, like, let's say that I have, 3D model of Darius, and now I move my camera. Does my model view matrix need to change? No, he's a perfectly good model from any angle. However, the projection matrix needs to change because I move the camera. And similarly, if my camera is staying alone and he's going crazy, then now we need to change maybe some of the model view things as we move up and down his hierarchy, but the camera projection stays the same. So it's just a nice sort of division of those two objects. Okay, so finally, after we do, by the way, this was a lot of slides to describe what? Essentially 3 matrix multiplies. Do you see that? Like essentially all that we've done so far, we took a triangle and we put its vertices into this canonical coordinate system. That's it. Now we got to draw the damn thing. So that's our next step, is to rasterize. In other words, figure out what pixels are lit. Okay, so when we do that, essentially there are many algorithms from rasterization. And if you took a graphics class maybe 15, 20 years ago, you would have probably spent your first 3 to 4 lectures on just different rasterization algorithms. I used to teach this stuff. The reality is that most of them don't happen in modern graphics cards anymore, which is a little depressing. Essentially, your graphics card is so good at parallel processing that, like, for instance, realizing that this row of pixels is shorter than that one is like less efficient than just drawing a giant box around the triangle and rasterizing the whole thing, because that's just like a giant sledgehammer that I can do fast. Which is really a downer, because some of these rasterization algorithms are really clever. So if you're bored, you should Google them. There's one called Bresenham's algorithm. You can rasterize any rational curve. But in any event, the basic problem that we're talking about here is called scan conversion. If you look at your graphics card architecture, we're going to do this in a couple weeks, which is one of the more painful lectures for me to teach because I don't like touching hardware. Essentially, this is one of very few pieces of your graphics card left that actually has a graphics purpose. Like most of your graphics card at this point is just a generic SIMD processor, but it is still worthwhile to do scan conversion and a few other things with built-in hardware. Essentially, the issue here, of course, is that your primitives, right, your triangles, they're continuous objects. They're like theoretical beasts sitting in Euclidean space. And at the end of the day, you have a discrete computer screen. You got to figure out what pixels to turn on. Right? That's your task here. And so that's, scan conversion or rasterization is just trying to figure out that list of pixels. Or if you want to sound fancy, you want to generate fragments. So a fragment is sort of like a pixel comma triangle pair, right? It's saying that like this pixel is in this triangle. So there can be multiple fragments in the same pixel. Do you see that? So like if I draw 2 triangles that overlap, I'll probably draw another fragment for each one. A very typical graphics exam question, if I were to think of one, which I guess I will, would be to like how many fragments are generated in this kind of a scene? And then of course one of the options will be, the width times the height of the screen. And that is the wrong answer, because it's not that you're just doing like one computation per pixel, right? But I digress. Okay, so there are many different ways to rasterize a triangle. The sledgehammer way to do it is to just look at every pixel on your computer screen and ask like thumbs up, thumbs down to the side of the triangle, which we've already more or less covered, right? So if you think of your triangle, as you should, as an object with 3 sides, then essentially the triangle is the intersection of 3 half planes, right? And so you can work through your math to come up with that binary test for like, given the vertices of the triangle, is this point inside or outside, by essentially doing 3 half-plane checks, right? And so that's essentially more or less the computation your GPU does right now. So in a little bit more detail, remember we already worked out the equation of a line looks something like this. This is an implicit equation, yeah? And so when you're inside of the triangle, maybe this thing is positive. But there's one detail here, which you've got to be careful that, remember that the A comma B pair here is the normal to your triangle. Remember we worked that out a couple weeks ago? I guess in this case, the normal to the edge. You need to make sure that that normal points in the proper direction, right? It points out. Because now we're doing a sign check, right? We're not just checking 0, which is what we did before. Okay, so anyway, really, rasterization is as simple as that. You construct these 3 functions for the 3 sides of the triangle, which you only have to do once, by the way, for the triangle. You don't do this per pixel. And then what do? You just say for every pixel, I evaluate E. Notice that is a SIMD operation. I'm doing the same computation for different pixels. The only thing that's changing is their XY location. And then I evaluate, and if all 3 of those have the same positive sign, I say thumbs up. That thing's inside of the triangle. Yeah? Right, so if you want to be pedantic about it, the first step of computing these 3 functions is called the triangle setup step, which is not terribly surprising. Yeah, and then you rasterize. Do we see any problems with this method? Yeah?
I mean, if you have like a 1 million pixel screen, then you're doing a million operations every time you want.
That's right. I could have a triangle which is less than the diameter of a pixel. And I could have a megapixel computer screen. And what does this algorithm do? It checks every single megapixel on the screen, well, every single pixel of the many pixels on the screen to check for that 1 pixel that I have to light up. Yeah, so that's what this picture looks like, right? I've got this giant triangle, and in fact, these 3 half planes do extend along the entire computer screen. But at the end of the day, I'm really not drawing all that much. So what can I do? Well, yeah, what can I do? Sorry, I'm getting excited here. How could I fix this? In a fairly SIMD way, yeah.
I mean, you have to have 3 vertices, so you can make a box around.
That's right. I can just draw a box on the triangle. That's probably a pretty reasonable thing to do. Does that always work? Thin, long triangles. In particular, Darius is absolutely right. Let's say that here's my giant computer screen. And I draw a triangle that looks like that. It's more of a boat than a triangle, but I think you get the idea. What will my bounding box be? Well, in this case, it'll be basically the entire screen, but of course, very few pixels are really being used up. So this is a heuristic that often works, but when you have bad geometry, maybe it's not so effective. Yep. So what do you do in that case? Well, often you just suffer. Yeah, of course, some graphics cards have very clever techniques for fixing that, but not all, actually. The kind of surprising thing is they're so fast that you really can throw away a lot of computation, and still it's better than more clever stuff. In any event, this particular technique is certainly very easy to code. There's one really, really, really annoying detail, which I used to give as an assignment, and everybody hated me, so I stopped. If you are bored one day, I encourage you to download the official OpenGL standards for rasterization, or I'm sure there's one for DirectX as well. And there's a really interesting case, which is what if this line precisely intersects that point? Is that point inside or out of the triangle? How many of us vote inside? How many of us vote outside? How many of us vote it depends? Yeah, so that's actually the right answer. Here's the issue. Let's say that I draw 2 triangles that share an edge. Yeah? So what's going to happen? I'm going to draw that edge twice, and it's going to intersect that pixel 2 times. But precisely. Yeah? And this actually can happen. It sounds stupid, but if I draw a vertical line, the odds of that happening are not so low, right? Well, there's going to be a problem, which is that I generated 2 fragments for this pixel, and now I got to decide which one's on top. That's not so clear. Or maybe even worse, I decide, oh, I rounded down a tiny bit, and now neither one of those triangles wants to own that pixel. Then what's going to end up happening? I'm just going to see whatever's underneath it. Yeah. And so if you read the standards for these things, you talk about engineering that no sane human being actually wants to do, but is somehow necessary. This is a great example of that, where like you need to come up with a very precise policy for rounding up and down to make sure that one fragment is generated for two triangles that share an edge all the way along the side of that edge. And that is a very difficult thing to do. Yeah. Anyway, if you want a really evil homework assignment, just draw two triangles that share an edge and guarantee that they never generate, more than one fragment per pixel. Yeah.
So I saw that we're like kind of sampling at the center of the pixel. Is there anything stopping us from like using the anti-aliasing stuff we learned about?
Yeah, there is, as a matter of fact. Yeah, so the question was, why not anti-alias? We'll talk about some anti-aliasing strategies for rasterization. What are the typical ones? They involve like generating random rays in every pixel. Can I do that anymore? Not really, right? Because I would need every pixel to have the same set of random rays, which is itself going to cause some weird aliasing effects. A pretty standard strategy would be rasterize your image like 3 times the size that your computer screen is, and then just make every pixel in the actual computer screen image like the average of that 3x3 patch. But obviously, from the signal processing point of view, like the anti-aliasing lecture we had, that's not an optimal thing. So there are some tricks around that, but they involve very different type of machinery. Like all this randomized, like just keep shooting rays until you get a reasonable number tricks, they don't work anymore. Yeah, so we're in a different universe here. Yeah. Any questions? So any ideas how we could do this a little better? Yeah. KD trees. So there's going to be a problem, which is I think accessing your KD tree data structure is really tricky on your graphics card because every pixel is going to need to traverse a different direction in the hierarchy. I believe there are some graphics methods out there, but they're quite advanced. Any other ideas? One optional thing we can do is rather than making a giant bounding box, we can go one row at a time. So in other words, rather than drawing the entire triangle, we're going to draw lines of pixels. Depending on your application, that can be faster or slower, but many people do implement that. And why is that? Well, we already talked, if you remember our lecture on accelerating ray tracing, we talked about how you can draw a straight line really easily in kind of a greedy way, like figuring out, do I move up or over in every step from a pixel? So, right, so I can actually implement those on the graphics card, and I know that they will take linear time in the size, like if this is an n by n image, it'll take at most n time, right? Or maybe n times square root of 2 or something. And why can I do that? Well, one thing I could do is rasterize the 3 sides of the triangle as straight lines, and then go back, and now for every scan line, I know the kind of beginning and end of the pixels that are inside the triangle, so I can do those row by row in a parallel fashion. Right? And so that's the standard technique people do. In fact, sometimes there's a really clever sort of pattern. I don't think, this is mostly just trivia stuff, like I wouldn't get hung up on this stuff. But for instance, some graphics cards will actually implement kind of a funny thing, which is they'll start at the top left pixel of a triangle, and they'll compute, and the whole time they'll be moving kind of down the triangle. So they'll keep track of the leftmost pixel and the rightmost one, and they'll move all the way to the rightmost pixel, and then they'll rasterize the next pixel down on the right side. They'll move there, and then they'll go this direction, and they'll kind of zigzag their way back. These kinds of algorithms are a little bit less relevant now that, again, your graphics cards are so parallel that any picture that looks like this, so that's like somehow giving you a sequence of pixels, is probably irrelevant. Which is disappointing, because they're really clever things. So if you're bored, like this is a funny old thesis. The guy's name is McCool, which is just great. Where they actually they use Hilbert space filling curves to rasterize a polygon. The idea being that the likelihood of leaving the inside is pretty low. But these are mostly tricks that mostly just don't occur anymore, so they're not worth getting too excited about. Yeah.
So to clarify, so that particular approach of trying to go use rasterize each line and then fill in the middle doesn't work because your GPU can't traverse back and forth across the screen.
Your GPU can. I mean, that's fine, right? Like you can have a for loop in your graphics card, but right. It means that when I parallelize, now the number of threads that I can run is equal to the number of pixels in that one row of the triangle. Whereas typically, your triangle, that number of pixels is pretty small relative to the number of threads that you can do on your GPU, which is in the hundreds, right? yeah, we'll see a few strategies around that. Essentially, these are things that change all the time, and sometimes they're proprietary. You can't even find the strategy people use. Okay, so those are some strategies. There's some questions you could ask, like, can we do even better? And of course, the answer is always yes. Here's another trick that people use, which is maybe we take our computer screen and we divide it into little blocks, and we parallelize this way instead. So now what I'm going to do is I'm going to like assign every thread in my graphics card like a 5x5 block on my computer screen, and then have it do just the brain dead version of rasterization inside of that block. Right? If you think about it, this is turtles all the way down, because the first thing I have to do is figure out which blocks intersect this triangle, which is just rasterization on a computer screen that's, I guess in this case, 4 times less big. Do you see that? So like you rasterize your triangle on a little grid, and then you use that to say, okay, these are the things that now I'm going to parallelize over to draw the insides of the triangle. So this is called hierarchical rasterization. And if you're looking for a really, really annoying thing to implement, you got it. These are really difficult to get right. And you talk about like rounding issues are really particularly gross here, right? Because you have to be quite conservative. But anyway, essentially, the point here, and the idea that you should be getting out of this is that like anything that you can do to reduce the number of threads that you have to spawn is a good thing. But if in order to do that, you introduce some serial computation, like this has to happen after that, then the people don't tend to like that on the graphics card, because your graphics card is really good at just launching a gajillion threads. That make sense so far? And again, these are algorithms that are worth knowing about, but if you find yourself implementing them, you better basically be working for NVIDIA. Like there's really very few reasons to do this at home, right? Like these are just built into your computer. And I give you guys a long list of references. I wouldn't be remiss if I did not mention all the beautiful algorithms that are out there for rasterization that were just really clever and totally irrelevant to your everyday life. Some of the sort of old school methods of doing that, basically, you know, you would rasterize the sides of the triangle, and then you kind of come up with these clever ways of walking back and forth along the scan lines, and they're just really smart. They're just too bad. Okay, so let's see here. There's one small detail that we omitted so far that's worth mentioning real quick. What happens if I rasterize a triangle behind my eyeball? Well, so far, it would actually be kind of tricky to detect in the rasterization pipeline. Do you see that? That like, essentially, for one thing, the vertex positions are going to invert, right? Because now I'm multiplying by a negative number when I do that rescaling. And that can cause some problems, right? So like, when I rasterize this vertex on my computer screen, what's going to happen? I'm going to move it through my eye, and it's going to look like over here somewhere, right? So like, not only is it, you know, going to be in the wrong place, but the depth isn't even that useful. And so that's really actually quite problematic. And it's funny, there are a lot of different things you can do. Can anybody suggest a really simple solution to this problem? Yeah.
I mean, regardless of what it draws, as long as you don't throw an exception, you're going to throw it away anyway, because the depth is behind the shear website. Right?
Yeah, so if you compute depth properly, you're okay. But let's say I have an unsigned depth value, because I don't want to deal with it anyway. Then I could run into some trouble. So one very simple thing to do is just like detect triangles that are behind the camera and don't draw them, right? I think that's the main technology. By the way, the case is even worse if like the triangle hits your eyeball exactly, then like God knows what happens. But right, so there are many things that people typically do, right? So like you've suggested, essentially the main thing that we do is clip. So once you compute your z value, rather than trying to insert it in the z buffer, if it's closer than that z near, you just reject your pixel. And so that leads to an interesting little piece of geometry in your 3D scene. It's called the ViewFrustum. And that's like sort of conceptually the cage that's holding in our cow here, right? Like, so this is all of the stuff that you could possibly see, right? And so this is the full frustum might be that like kind of cone coming out of your eyeball, and then I clip it at the near and far planes. And so there are a lot of different reasons to clip. I mean, one is it avoids some degeneracy. You don't draw stuff too far away. Remember that our z value is actually 1 over z because we've homogenized. So this avoids division by 0. And moreover, there's very simple thing, which is, of course, if your entire bunny has a bounding box outside of your ViewFrustum, then you just shouldn't send it to your graphics card, right? This is like the world's stupidest optimization, but it took people like a weirdly long time to to get this stuff right, because you have to double check, does this box intersect this funny shape? There's kind of a funny, like, a lot of the graphics technology advanced because like somebody wanted some kind of effect or visual thing they couldn't capture, and then they had to come up with a clever algorithm. There's also a little bit of an instance of algorithms affecting art when it comes to these sorts of techniques. So like a lot of the old video games where rasterization was more expensive than it is now took place in like dungeons and mazes and things. Why would that be? Yeah. You got it. So like oftentimes these video games would have these little tiny entrances between different rooms because it was very easy to clip stuff outside of the other side of the wall, right? So you could work out like, anything that is not in this room or the room adjacent to it, I never have to rasterize, so I'm never going to send it to my graphics card, right? And so it's actually kind of a funny thing that like, if you look at the layouts of the levels of old video games, partially they were designed to make your video game fun, partially they were designed to make rendering easier, right? Because they wanted to bound on the number of triangles that they would have to rasterize at any given time. Right. So the slides also go through another technique called homogeneous rasterization. I don't think this is terribly exciting. Essentially, the only point of homogeneous rasterization is the way we've talked about it so far. It's a purely 2D computation, but where things get a little complicated is like if this triangle like starts in front of the camera and then like goes past your face or something, then you have to be a little bit careful with your bookkeeping. A different thing that some people do in the homogeneous setup is say, well, actually, the sides of my triangle, if I look at a side, right, which is defined by 2 points, and I add a third point, which is my eyeball in 3D, then this actually defines a whole half space, right? And so in some sense, if I think about a triangle like sitting in front of my eye, and I draw these planes through my eye and through the sides of the triangle, I get like a little cone sitting in 3D, right? And anything inside of that are sort of stuff that I might potentially draw, right? And so in the homogeneous rasterization setup, you actually do that computation in 3D. So you kind of walk along the side of the triangle instead of the image plane. I don't think it's worth going over a ton of detail, but essentially all it does is works through the equations of the plane instead of the equation of the triangle, and then computing z. And this is kind of nice because it works for stuff behind your eye and so on. So what this removes is needing to do clipping explicitly, because you really are just keeping track of depth as you draw this thing. But I think these are basically implementation details. I don't think there's a whole lot to worry about here. So in any event, what have we done so far and what have we not done? So far we have what? We have projected the vertices of our triangle into the computer screen. We've figured out which pixels to light up. Now what do we have to do? We have to light the damn thing. And this is the one piece of this pipeline that's basically unchanged from ray tracing, right? Because now you've detected, basically you have your hit detection of some sort, and what are you going to do? You're going to evaluate your BRDF per pixel. You have your normal to your triangle. You got all the information you could want, and now you evaluate that function. And that is a massively parallel thing, right? That's perfectly fine to do in a SIMD way. So later on, we're going to talk about pixel shaders. This is a misnomer. You can run multiple pixel shaders in the same pixel, right? Because remember that if I draw two triangles that overlap, they will both generate fragments for the same pixel. Yeah, I'm gonna repeat that a few times. Modern graphics hardware, it's pretty cool. Like essentially, there's this programming language, GLSL, which you guys are going to code in, which is a programming language in a programming language, right? It's like a little language for coding up shaders to do this kind of computation. And what you do is you write a little function, and then that function just gets applied to every single pixel on your screen. And your modern hardware can execute some pretty complicated programs inside of GLSL, which include, like evaluating integrals and doing all these BRDFs. What can they not do is send a secondary ray, right? All they can do is just complicated things per pixel that require no information about the rest of the universe. So that's where things get a little complicated. the other thing that they can't do, oftentimes, and we're going to talk more about this later, again, the priority in this area is SIMD processing. I just want to keep hitting everything with the same hammer. So for instance, if statements, you know, like if this pixel's coordinate is even, then I'm going to color it green. If this pixel's coordinate is odd, then I'm going to do this. If you think about it, that could be quite problematic, right? Because in if statement, like branching, what is it doing? Well, it's saying that, you know, some pixels are treated differently from others, and your graphics card doesn't know how to do that. It wants every pixel to do the same thing. So there's a kind of an interesting thing, which is like maybe I'm rasterizing my scene, and like there are like 10 pixels in the scene that I want to be a different color, and I write just like one shader that does the whole scene and says like, if I want one of these 10 pixels, draw it this way. What do you think is going to happen? Anybody know what happens behind the scenes in your graphics card typically? It's kind of funny. Your graphics card will actually execute both sides of the if statement and then have a line of code that just chooses the output that's relevant, because that is SIMD processing, right? It's saying do the same computation everywhere and then just throw it away if I didn't actually need it, because that is more efficient than actually branching. Modern graphics cards, it turns out, can do a little bit of branching, but often not much. Similarly, if I have a for loop inside of my shader, what do you think it does? It literally Control-C, Control-V's your code that many times, and that's what it executes. So it's kind of funny, when you code on this stuff, it like looks like a normal programming language, but you'll make some change to your code that like seems cosmetic, and suddenly it will grind to a halt. And that's the reason that like the architecture here is quite different from what we're used to. All right, so in any event, yes? Yeah.
How similar is it to the daylight thing that's being made, that was made by Fredo?
Yeah, Fredo and Jonathan Reagan Kelly, who actually just today is here. He is going to be starting on our faculty in a couple months. Halide is, let's see, that's a general purpose programming language for image processing, right? So I think it leverages a lot of GPU stuff. I don't know the details. I imagine they're quite similar in spirit because they do want to leverage GPU computation, but I don't know. You should ask Fredo. Yeah. I don't know. My programming language stuff is too discrete for me. I like real numbers. Okay. So right. So now that we've computed our per pixel color, we've got to update our frame buffer. Incidentally, this is like super close to hardware, what we're doing, right? Because this is happening 30 times a second. I don't have time to like do fancy high-level stuff. When I say buffer, literally there's a piece of memory on your graphics card that your computer screen is looking at and just drawing. So there's a bit of a problem here, which is I'm drawing one triangle at a time. What would happen if like, you know, I have one thing coming in, which is the stuff I'm drawing, a thing going out, which is going to my computer screen. You could imagine a world in which I draw a triangle and then I draw one triangle at a time, and what do I see on my screen? I see one triangle appear at a time. That's not so great. So typically your graphics card has two buffers, it's called double buffering, for obvious reasons, and a bit. And what does it do? It says, this bit tells the computer screen to draw this one, and it says my rasterization tool is going to draw over here. And then once you're done rasterizing, you flip that bit, those two roles change, and that way you never see the process of drawing happening, right? So this is a nice technique. But in any event, right, so our very last thing we got to do is visibility checking. And of course, this is really critical. Visibility can be really complex. This is something that, it's funny because like now it just seems totally obvious. If you look at the history of computer graphics, there was a long period of time when people were using a technique called the painter's algorithm, which I think is great. It's like a, what's the word I'm looking for? It's like a politically correct term for just a stupid algorithm. So the painter's algorithm is just like drawing one object at a time, and it just always is drawing it on top. And this is really problematic. Like even in 2D. So for instance, let's see if I can manage to draw this. Every year I try, and every year I fail. So let's say that I have 3 sticks, right? And here's so here's a stick. And then here's another one that's sitting on top of it. And now here's a third, which is going to go underneath this guy. Did I do it right? Oh, I did it right. Yay. Okay, here you go. Can I draw this scene using the painter's algorithm? No, right? There's no ordering of these three objects that I can choose, assuming I did it right. Oh, I did it right. I can draw them one at a time, right? And so this is a big issue. So there were a bunch of algorithms out there. It was funny. People were like putting lipstick on a pig for a long time. Like they would like have these clever algorithms for like trying to order the objects in your scene so that the painter's algorithm would be approximately correct. But then Ed Catmull and company came in and they said, aha, the depth buffer is really what we need to go from stuff like the left-hand side to the right. And really it's quite simple, right? So, you know, when we were doing raycasting, we maintained our intersection with the closest object. That doesn't quite work anymore because we're iterating over objects on our outer loop. So instead we just have this Z buffer value, right? So essentially, Z buffers behind the scenes look something like this, right? So like, you know, I'm rendering my house, so it has a nice green lawn, but of course the reality is that the lawn is facing away from the camera, so the depth is getting bigger. And so that's what's happening behind the scenes. This is our first example of a buffer that we store, but we don't draw, right? Which is kind of a funny thing. Like we're drawing some stuff, but not all of it is intended for your computer screen. Right, and so the Z buffer, as obvious as it sounds now, really was a big breakthrough in computer graphics technology because it allowed you to draw scenes like this one. In fact, I think if you look at some old icons, they actually are exactly this object just because they're showing off a little bit, you know? Right, and so the Z buffering algorithm is quite simple, right? So you're drawing all of your scenes and you just compute your current Z, and if you know, you don't pass the Z test, you just throw it away. And so that works for our nice test case. So here's a nice example of what that looks like. Yeah.
Sorry, how would transparency complicate visibility?
That's a great question. Yeah, what do we do with transparency? Yeah.
You draw that, and then as you're drawing it again, you look at the current value and the color buffer, and then you add it to it in some sort of bundle.
Yeah, so that's one thing you could do heuristically, right? In other words, like somehow transparency just doesn't count for depth. The reality is that there's no good answer there. Yeah, and like for instance, a refractive surface, like you just give up. Yeah, no, transparent objects are a problem for depth buffering because they're, and that's why like when you look through video game windows, they tend to be like basically just a shading on top of the image rather than like anything clever, right? Because that's all you can do. Yeah. So I think typically transparent objects, you just wouldn't update the Z buffer when you draw them. Yeah. You can go down your list of visual effects and ask like, what does that do to the Z buffer? And pretty soon you'll start punching holes into stuff. Like, for instance, what about a reflective object? Well, what's the Z buffer then? Because somehow now I need to deal with like occlusion of the stuff on the object that my light rays reflected off of. So that's not so clear, right? So the typical thing to do is A, limit the number of reflective objects in your scene to a very small number. And then for each of those, maybe what you do is you first rasterize the side of the reflective object from the perspective of the object, the really weird camera projection. And then rather than doing any depth buffer lookup at all, you just say, aha, now I put this like weird texture on that shape, which I got by rasterizing the other way. These are the sort of hacks that we have to do. Right, so next time we'll think about a lot of other problems here. One thing we haven't addressed is texture mapping. Texture mapping is pretty parallelizable. And so it's really not going to be a big deal. You're just going to have to be careful with your coordinates because now you're kind of rasterizing two triangles at the same time, right? One in the scene that you're drawing on the screen, and then the other in the texture grid. That makes sense? All right, so any questions for today? I think we'll end a little early. It's nice now that our previous class is scared into ending on time. My lecture's ending early. Yeah. All right, guys. So with that, I'll see you on Thursday. We'll talk even more about rasterization. Get excited. Seriously, try your homework assignments. They don't always work. This is the one that always fails. Yeah. So have a good week.